The night sky over Anzio erupted in a rhythm that defied every instinct Sergeant James Reeves had learned in 2 years of anti-aircraft warfare. It was the 22nd of February, 1944, and his battery was firing not in desperate bursts, not in the chaotic spray and pray pattern he knew from North Africa and Sicily, but with a mechanical precision that felt almost inhuman. Every 5 seconds, another shell left the barrel. Every 5 seconds, the gun traversed exactly 3 degrees, and every 5 seconds, somewhere in the darkness above the beachhead, another German bomber adjusted its course or fell from the sky. What disturbed Reeves most was not the noise. Though the 90mm guns shook the ground with each report, it was the silence between the men. No shouting, no frantic cranking of the manual traverse wheels, no desperate attempts to lead the target while calculating altitude, speed, and deflection in your head while tracers lit the sky and bombs whistled down. The crew simply loaded, and the gun, guided by a box of electrical components the size of a refrigerator sitting 20 feet away, did the rest. They were servants to a machine that thought faster than they could, and it was saving their lives while making them obsolete. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. 3 months earlier, Reeves would have called it witchcraft. The technical manual called it the M9 gun director, paired with an SCR 584 radar unit. The men called it the mechanical brain, and when it first arrived at their position in southern England in November of 1943, they wanted nothing to do with it. The problem with fighting in 3 dimensions is as old as aerial warfare itself. When a man aims a rifle at a running deer, he must lead the target point, not at where the animal is, but where it will be when the bullet arrives. This is intuitive, learned through practice, manageable at distances measured in dozens of yards. But when the target is an aircraft at 15,000 feet, traveling at 250 miles per hour, and your shell takes 13 seconds to reach that altitude, the mathematics become punishing. By 1943, anti-aircraft gunnery had evolved into a strange synthesis of physics, probability, and industrial coordination that still relied heavily on human calculation. A typical American 90mm anti-aircraft battery consisted of 4 guns, served by crews of 9 men each, coordinated by a director crew equipped with optical rangefinders and mechanical computers. The director crew, usually positioned in a separate pit with unobstructed views, would track the target through their instruments, calculate altitude, range, and bearing, then transmit these settings electrically to the guns. The gun crews would manually set their weapons according to these instructions, then fire. This system, refined through decades of development, represented the pinnacle of conventional fire control. It was also maddeningly inadequate. The fundamental constraint was time. From the moment a target was acquired to the moment a shell burst near it, 12 to 15 seconds elapsed under ideal conditions. In that time, the aircraft moved nearly a mile. The director crew had to predict not just where the aircraft was going, but where it would be at the precise moment the shell arrived at that altitude, a problem complicated by wind drift, air density, the ballistic characteristics of the shell itself, and the simple fact that aircraft rarely flew straight and level when being shot at. Even under perfect conditions, clear weather, steady targets, experienced crews, a conventional anti-aircraft battery firing at a single bomber at 15,000 feet had roughly a 2% probability of scoring a hit with any individual shell. This was not due to poor training or inadequate equipment. It was the brutal mathematics of trying to hit a moving point in 3-dimensional space with another moving point, when both points were separated by miles and your tools for measuring their relative positions were updated only every few seconds. The limitations revealed themselves most starkly at night. Optical rangefinders were useless. Searchlights could illuminate targets, but coordinating searchlights with guns was its own nightmare, and a single aircraft could slip between searchlight beams. Sound locators, massive concrete or metal horns that operators used to track engine noise, provided crude directional information but no range data. And sound travelled slowly enough that the aircraft had often moved by the time its engines were heard. The result was that night raids, particularly by fast bombers flying above 12,000 feet, faced minimal effective resistance from anti-aircraft fire. Crews fired on instinct, sound, and hope, expending hundreds of shells for each aircraft damaged. This was the tactical reality that governed anti-aircraft warfare from London to Leningrad, from Pearl Harbor to Berlin. You could thicken the air with steel and fire, you could train your crews to mechanical perfection, but at the end of the night, you counted your shells expended and your targets escaped and accepted the ratio as a law of physics. And then, in the autumn of 1943, the law changed. The device that arrived at Sergeant Reeves's battery position outside Portsmouth looked to his practiced eye like a collection of components that belonged in 3 different vehicles. There was a trailer-mounted radar antenna, a rectangular grid affair about 6 feet tall that rotated on a powered mount. There was a generator unit, rumbling diesel loud, feeding power to the whole assembly. And then there was the M9 Director itself, housed in a boxy trailer that the manual claimed contained 360 vacuum tubes, 40 relays, and enough electrical circuitry to predict the future. The technical representative from Bell Laboratories who supervised the installation was a civilian named Morrison, thin and pale in a way that suggested he had spent the war in laboratories rather than fields. He spoke with the careful diction of an engineer addressing soldiers, always aware that his vocabulary exceeded theirs, but trying not to be insulting about it. The radar transmits pulses, Morrison explained to Reeves and the battery commander, Captain Halloran, as they stood in the cold November drizzle watching his team run cables. When those pulses strike an aircraft, they bounce back. By measuring the time between transmission and return, we're talking microseconds. Here the system calculates range automatically. The antenna is mechanically linked to the director, so we also get bearing and elevation. How's it different from what we've been doing? Halloran asked. He was a West Point man, artillery through and through, skeptical of anything that couldn't be explained with a slide rule. 3 ways, Morrison said, holding up fingers. First, it's automatic. The radar locks onto the target, and the director continuously updates firing solutions without human calculation. Second, it's fast. New data every revolution of the antenna, that's about 2 seconds. Your current optical system updates maybe every 5 to 10 seconds, and only if your crew is very good. Third, it works in any weather, day or night, smoke or clouds. The radar doesn't care. Reeves watched the antenna rotate, its mechanical hum steady against the wind. And it just tells the guns where to point. Not just where to point, Morrison said. Where to point and when to fire. The M9 calculates the future position of the target, where it will be when your shell arrives, and continuously updates that solution. The guns track automatically. Your crews just load and fire on command. It sounded, Reeves thought, like something from a Buck Rogers serial. Automatic tracking, continuous calculation, mechanical prediction. And all of it dependent on electrical components that, in his experience, failed whenever exposed to moisture, vibration, or sustained use. What's the failure rate? He asked. Morrison smiled thinly. We're working on it. The first live fire test happened on a grey afternoon in December, with a B-24 Liberator flying a predetermined pattern at 12,000 feet, towing a target sleeve. The battery Reeves's crew on Gun 3 was tasked with tracking and engaging the sleeve using the new system. The rest of the battalion turned out to watch, standing in clusters at a safe distance, smoking and speculating. The radar acquired the target at 8 miles, a green blip on the oscilloscope screen that Morrison and his team monitored inside the director trailer. Reeves, standing at his gun, watched the barrel begin to move on its own, elevating and traversing smoothly, powered by the electrical servos that now controlled it. The sensation was eerie, like watching a puppet move, knowing there were strings but unable to see them. Target locked. Morrison's voice came through the headset, calm and technical. Tracking solution updated. Guns are hot in 10 seconds. The B-24 droned overhead, visible now, towing its bright orange sleeve 1,000 feet behind. Reeves's crew stood ready, shell loaded, waiting for the command to fire. The gun continued its smooth traverse, leading the target by what looked to Reeves like an absurd amount, 20 or 30 degrees ahead of where the sleeve actually was. "Fire," Morrison said. The gun roared. The shell departed. 5 seconds later, another shell loaded, and the gun fired again without any adjustment from the crew. Then again, and again. 12 rounds in 60 seconds, each one fired automatically when the director determined the solution was optimal. Reeves didn't see any hits. The bursts were too far away, small black puffs against the grey sky. But Morrison, monitoring the radar return, noted that 3 shells had passed within 50 feet of the sleeve. On a combat target, an aircraft, rather than a small piece of fabric that would have been 3 kills or critical damages out of 12 rounds fired. The math was staggering. Traditional doctrine held that it took several thousand rounds of anti-aircraft fire to down a single aircraft. This test suggested the new system might do it with a few dozen. Captain Halloran, watching from the director's position, asked the question everyone was thinking: does it work this well in combat? Morrison closed his notebook. "That," he said quietly, "is what we're about to find out." The answer came in January of 1944, though not in England. The first full battery of SCR 584 and M9 equipped guns went to the Mediterranean, deployed to the Anzio beachhead where German air attacks were methodical and relentless. The beachhead, carved out of the Italian coastline 30 miles south of Rome, was supplied entirely by sea. Every ton of ammunition, every ration, every replacement soldier came in through the port. The Germans knew this, and their bombers came every night, Junkers, 88 seconds mostly, sometimes Heinkels, flying at 10 to 15,000 feet, where conventional anti-aircraft fire was ineffective. The new radar batteries arrived in February and were operational within days. On their first night of combat, they tracked and engaged 11 separate raids. The results, transmitted back through channels and eventually reaching Reeves's battery in England, were almost difficult to believe. In 7 hours of darkness, the 4-gun battery had fired 412 rounds. They had confirmed 3 aircraft destroyed, 2 probably destroyed, and 4 damaged. The German raids decreased in frequency within 48 hours. Within a week, Luftwaffe bombers changed their tactics entirely, approaching the beachhead at wave-top level to stay below the radar coverage, accepting the increased danger from smaller caliber guns rather than face the 90mm guided by mechanical prediction. The ratio of shells to kills had improved by a factor of 10. The psychological effect was larger still. By March of 1944, when Reeves's battery crossed the Channel as part of the build-up for the invasion of France, the mythology around the radar-directed guns had already taken root. Men who'd never seen the equipment spoke of it in tones usually reserved for wonder weapons. Stories circulated, some true, some embellished, about single batteries holding off entire Luftwaffe squadrons, about German pilots refusing to fly over positions marked by the distinctive rectangular radar antenna, about shells following evasive aircraft through turns and climbs as though guided by invisible wires. The reality, as Reeves discovered during the first week in Normandy, was both more impressive and more complicated than the stories suggested. The SCR 584 radar operated on a wavelength of 10 centimeters, what engineers called S-band, transmitting pulses of electromagnetic energy at a rate of 1700 per second. Each pulse lasted a few microseconds. When these pulses struck an aircraft's metal skin, a tiny fraction of the energy reflected back to the receiving antenna. By measuring the time delay, the few millionths of a second it took for the pulse to travel to the target and return the system-calculated range automatically with an accuracy of plus or minus 25 yards. This was precision that no optical rangefinder could match, especially at night or through clouds. But the radar's true innovation wasn't its range-finding capability. British and German systems had already demonstrated radar's utility for detecting aircraft. The revolution lay in what happened to that information after it was received. The SCR-584 was mechanically linked to the M9 gun director through a system of electrical servos and data transmission lines. Every 2 seconds, as the radar antenna completed one rotation, new position data flowed into the director's computing mechanism. Inside the M9's trailer, a maze of vacuum tubes and mechanical calculators performed a calculation that would take a trained human crew 30 to 40 seconds. It compared the target's current position with its position 2 seconds ago, calculated velocity and bearing, factored in altitude and expected ballistic trajectory, and predicted where the target would be at the moment. A shell fired right now would reach that altitude. Then it did the calculation again, and again, continuously updating the solution 50 times per minute, adjusting for every slight change in the target's course or speed, compensating automatically for wind, air density, even the Earth's rotation at high angles of fire. The gun crews became, in effect, mechanical loaders in a system that thought faster than they could. The process Reeves had trained for the careful triangulation, the manual cranking of elevation and traverse wheels. The gunner's intuition about when to fire was replaced by servo motors that moved the gun barrel smoothly from target to target, and an electrical firing circuit that triggered the round at the mathematically optimal moment. The first night the system fired in anger over Normandy, Reeves's battery engaged a Heinkel 111 at 14,000 feet. The bomber was invisible to the naked eye, hidden above clouds, identified only by the steady blip on the radar screen and the distinctive asymmetric pulse of its engines picked up by the sound locators. The guns fired 23 rounds in 2 minutes. The radar tracked the target through each salvo, adjusting the firing solution as the bomber attempted evasive maneuvers. On the 23rd round, the blip disappeared from the screen. No one saw it fall. There was no visual confirmation, no wreckage to inspect in the morning, but the radar return vanished, and the sound of engines ceased, and that was as close to certainty as war allowed. The statistical improvement over conventional fire control was documented meticulously in after-action reports that filtered back to the War Department and the British Air Ministry. A traditional 90mm battery, firing at aircraft at 10 to 15,000 feet with optical directors, required an average of 2,400 rounds to achieve a single confirmed kill. The same battery, equipped with SCR-584 and M9, required an average of 150 rounds. But statistics, however dramatic, didn't capture what the technology actually meant to the men who operated it. The change was psychological as much as tactical, a fundamental shift in the relationship between the gunner and the target. In conventional anti-aircraft warfare, crews fired with the knowledge that their chances of hitting any individual target were negligible. You fired because doctrine demanded it, because volume of fire might force the bomber off its run, because doing something was better than doing nothing. But you didn't expect to hit. The expectation was cumulative enough. Batteries firing enough shells over enough time would down enough aircraft to matter strategically. Individual shots were essentially random events. The radar system inverted this logic. Now, when your battery fired, you expected results. The radar locked on, the director calculated, the guns fired, and more often than not, the target altered course or fell. Sometimes you saw it happen, a wing folding, a fireball spiraling down. Sometimes you only saw the radar return disappear. But you saw consequences, immediate and causal, linking your actions to outcomes in a way that conventional fire never had. This bred a particular kind of confidence that commanders found both useful and concerning. Useful because confident crews performed better, maintained their equipment more carefully, fired with discipline rather than panic. Concerning because the system's reliability made its failures when they happened harder to accept. The failures were inevitable, given the complexity. 360 vacuum tubes meant 360 potential points of failure. Each tube generated heat, and heat shortened tube life. In the damp climate of northern France, moisture infiltrated electrical connections. Vibration from the guns firing loosened relays. The radar's rotating mechanism, exposed to the elements, required constant maintenance. The generator that powered the entire system consumed fuel at a prodigious rate, nearly 15 gallons per hour, and if the generator failed, the entire fire control system went dead, reducing the battery to manual operation with optical backups that most crews were by now poorly practiced in using. Sergeant Morrison, the Bell Labs civilian, had stayed with the unit, nominally as a technical advisor, but functionally as the only person who truly understood the system's innards, spent most of his time troubleshooting. He carried a worn notebook filled with diagnostic procedures, voltage readings, timing sequences. When the system failed, he disappeared into the director trailer with a voltmeter and a set of spare tubes, emerging hours later with specific culprits. Tube 14 in the range circuit, or relay number 6 in the servo controller. The crews learned to view the system as temperamental, not unreliable, but moody, requiring attention and care. You checked the antenna rotation mechanism every 4 hours. You monitored tube temperatures. You kept spare generators fueled and ready. In return, when the Luftwaffe came, the system performed. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. By June, as Allied armies pushed inland from the Normandy beaches, the character of the air war shifted. The Luftwaffe, battered by sustained attrition and fuel shortages, launched fewer and fewer conventional bombing raids. When German aircraft appeared, they came low and fast. Focke-Wulf, 190 seconds on strafing runs, approaching at treetop level where radar coverage was blocked by terrain and buildings. The SCR-584 could track low-flying aircraft if it had line of sight, but its minimum effective range was about 500 yards closer than that, and the geometry of the system broke down. A fighter bomber at 200 feet altitude, traveling at 300 miles per hour, covered 500 yards in less than 4 seconds. By the time the radar acquired it, calculated a firing solution, and directed the guns onto target, the aircraft was already past, hammering ground positions with cannon fire or dropping bombs. This tactical adaptation, flying beneath the radar's optimal envelope, forced anti-aircraft batteries back toward manual operation and visual targeting for low-altitude threats. The 90mm guns, designed for high-altitude work, proved awkward in this role. Their rate of fire was too slow, their traverse speed inadequate for tracking fast-moving targets at close range. Smaller caliber weapons, the 40mm Bofors, the quad-mounted 50-caliber machine guns became more tactically relevant. The radar system hadn't become obsolete, but it had become specialized, optimized for a type of warfare that the Germans were increasingly unable to wage. As Allied air superiority solidified over France, the primary targets for anti-aircraft fire shifted from Luftwaffe bombers to V-1, flying bombs, the pilotless jets that Germany launched by the hundreds against London and Antwerp. The V-1 presented a unique challenge for the radar-directed guns. It was fast, roughly 400 miles per hour, but it flew straight and level at a constant altitude between 2,000 and 3,000 feet, following a gyroscopic guidance system that couldn't evade. It was small, with a radar cross-section smaller than a bomber, but large enough for the SCR-584 to track reliably, and it was coming in numbers that made every intercept tactically significant. In August of 1944, Reeves's battery was repositioned to the Belgian coast as part of a defensive belt established to intercept Von II, targeting Antwerp. The port city had become the primary logistics hub for Allied forces pushing into Germany, and the Germans understood its value. In the autumn of 1944, they launched more than 2,000 Von Second toward Antwerp. The defensive system was layered. Fighters patrolled the outer zones, attempting to shoot down the missiles or tip them over with wingtip strikes. Closer in, anti-aircraft guns, both conventional and radar-directed, created a barrier of fire. The radar batteries were positioned along the coast, with overlapping coverage designed to track each missile from the moment it crossed the shoreline until it was destroyed or passed into the interior zones defended by other batteries. For the crews, V-1 intercepts were mechanically simpler than engaging manned aircraft. The missile didn't evade, it didn't vary in altitude, its speed and course were predictable. But the tactical pressure was immense. Every V-1 that got through carried a 1-ton warhead into a city packed with military personnel and civilians. Miss rates weren't abstract statistics. They were explosions you heard in the distance, columns of smoke rising over neighborhoods. The radar system excelled at this work. The SCR-584 could track a V-1 from 15 miles out, giving the M9 director ample time to calculate an intercept solution. The battery would typically engage at 8 to 10 miles, firing continuous salvos as the missile approached. The guns could fire 12 to 15 rounds per minute per tube. 4 guns meant 48 to 60 rounds per minute, all converging on a target following a predictable path. Reeves's battery, over a 2-week period in September, engaged 37 Von Second. They destroyed 23. Damaged 7 others sufficiently that they crashed short of the city, and recorded 7 complete misses. The success rate 80% destroyed or diverted was better than any conventional fire control system could have achieved, but it still meant that roughly 1 in 5 missiles got through. The moment that crystallized the system's capabilities and its limitations came on the night of October 9, 1944. The Luftwaffe, in a rare massed effort, launched a coordinated raid against Antwerp using both conventional bombers and Von Second. The bombers Ju 88 seconds and He 111 seconds, flying in loose formations at 12 to 15,000 feet, were intended to saturate the defences while the flying bombs came in low. Reeves's battery, positioned on a slight rise 3 miles inland from the coast, had radar coverage of both approach routes. At 2200 hours, the SCR-584 began picking up multiple contacts. Morrison, monitoring the scope, counted 8 distinct targets, 5 at high altitude, moving slowly, almost certainly bombers, 3 at low altitude, moving fast, certainly Von Second. This was the scenario the system was designed for. Multiple targets, simultaneous engagement, continuous tracking and fire direction. The M9 director could handle up to 8 targets in its memory, assigning priority and cycling between them, providing firing solutions for whichever target posed the most immediate threat. Engaging high-altitude group first, Morrison announced through the headset. Target Alpha, bearing 285, range 12 miles, altitude 14,000. Guns assigned. Fire when ready. The 4 guns elevated in unison, traversing to the calculated bearing. The crews were loaded. The electrical firing circuit, triggered by the director when the solution was optimal, sent current to the firing pins. 4 shells departed simultaneously. 5 seconds later, the guns fired again, the director having updated the solution based on the target's movement. Then again, and again. Target Alpha hit, breaking up, Morrison reported, his voice steady. Target Bravo, bearing 290, range 10 miles, altitude 13,000. Engaging. The guns swiveled to a new heading. More shells. The rhythm was mechanical, relentless. Each gun firing every 5 seconds, 4 guns cycling through targets as the director assigned them. Load, fire, load, fire. The brass casings piling up in the gun pits, the barrels heating even in the October cold. Targets Delta and Echo low-altitude contacts entering range. These are Vone second, shifting priority. The guns depressed, tracking down from high-altitude bombers to missiles skimming at 2,000 feet. The shift was seamless, executed by the servos without human intervention. The crews simply kept loading, trusting the system to know which target needed, killing next. Over the next 45 minutes, the battery engaged all 8 targets. They fired 207 rounds. They destroyed 3 confirmed bombers, damaged 2 more, and shot down 2 of the 3 Vone second. The 3rd missile got through their coverage zone and was destroyed by a battery further inland. When the all-clear sounded at midnight, Reeves stood in the gun pit, ears ringing despite the cotton stuffed in them, and looked at the pile of spent brass casings. 200 shells in less than an hour. In the system's absence, in the careful, deliberate world of manual fire control, they might have fired half that number and hit nothing. The mathematics of warfare had been rewritten by vacuum tubes and electrical circuits, and the old certainties that the sky was large and aircraft were small, and hitting anything was mostly luck no longer applied. Captain Halloran, climbing out of the director pit, found Morrison making notes in his perpetual notebook. "How many tubes did we burn out?" Halloran asked. Morrison didn't look up. 17. I'll replace them in the morning. Will we have enough spares?" "Until we don't," Morrison said. He closed the notebook. "The system works, Captain, but it's not magic. It's 360 vacuum tubes, and every one of them is dying a little bit every time we fire. The degradation was cumulative and ultimately predictable. Vacuum tubes had finite lifespans measured in hours of operation. In laboratory conditions, a quality tube might last 1,000 hours. In a trailer bouncing across European roads, exposed to moisture, vibration, temperature swings, and the electromagnetic noise generated by nearby transmitters, that lifespan dropped to a few hundred hours. The SCR-5, 8-4 and M9 system, running continuously, consumed tubes at a rate that supply chains struggled to match. By November, as the Allied advance slowed in the face of winter weather and stiffening German resistance, maintenance became as important as operation. Batteries rotated off the front line not because they were combat ineffective, but because their radar systems were running on half strength, with backup tubes substituted for optimal tubes, critical circuits jury-rigged to compensate for components that no longer met specifications. The War Department, recognizing the supply problem, established dedicated tube replacement facilities in England and France. Damaged tubes were shipped back, tested, and either refurbished or scrapped. New tubes came forward in priority shipments, sometimes by air. But the consumption rate exceeded production, and by December of 1944, some batteries were operating with degraded capability able to track and engage targets, but with reduced accuracy and slower solution times. Reeves's battery, after 6 months of nearly continuous operation, was pulled back to a rest area outside Brussels in mid-December. The guns were still functional, but the SCR-584 was limping. The M9 director calculated solutions, but slowly, with occasional errors that Morrison diagnosed as failing tubes in the computation circuits. They could still fight, but not at the mechanical perfection that had become normal. "It's like watching someone get old," Reeves said to Morrison one evening as they stood near the director trailer, watching the antenna rotate in its perpetual circle. "Still works, but not like it used to." Morrison, hands shoved in his coat pockets against the December cold, nodded. "We built something remarkable," he said. "But we built it with parts that were never designed for this kind of abuse. Every tube has an expiration date. The whole system is slowly burning itself out. Can it be fixed? With enough time and enough replacement parts, sure. But time is the one thing we never have enough of." The test came 16 days later, in circumstances that no amount of preparation could have anticipated. On December 16, 1944, German forces launched their last major offensive in the West, a massive assault through the Ardennes forest aimed at splitting the Allied armies and recapturing the port of Antwerp. The offensive achieved complete tactical surprise. Within 48 hours, German armor had penetrated 20 miles into American lines, and the entire front was in chaos. The weather was the Germans' greatest ally. Low clouds, fog, and snow grounded Allied aircraft for the critical first week of the offensive. The tactical air superiority that had dominated European skies since D-Day vanished behind a ceiling of grey clouds that sat at 600 feet and refused to lift. German tanks and infantry moved in daylight, unmolested from above, pushing back American units that had grown accustomed to calling in airstrikes whenever they encountered serious resistance. For the anti-aircraft batteries, including Reeves's unit, hurriedly repositioned to cover the northern shoulder of the German penetration, the weather created a paradox. There were no high-altitude targets because there was no high-altitude visibility. The Luftwaffe, taking advantage of the cloud cover, flew ground attack missions at 200 to 400 feet, ducking in and out of cloud banks, hitting Allied supply columns, and retreating units with rockets and cannon fire. The SCR-584 radar could track these aircraft, but its optimal engagement envelope targets at 8 to 15,000 feet, approaching on predictable vectors, no longer existed. Everything was happening at altitudes where the radar was marginally effective, and the 90mm guns were awkward and slow. Morrison spent the first 3 days of the offensive trying to recalibrate the system for low-altitude work. He adjusted the radar's minimum range settings, modified the director's calculation parameters to account for shorter engagement times, even experimented with different fusing on the shells to get airbursts at lower altitudes. But the fundamental problem remained. The system had been optimized for a type of warfare that weather and German tactics had temporarily made obsolete. On December 19th, the battery engaged a flight of W-190 seconds, attacking a supply convoy 2 miles west of their position. The radar acquired the aircraft at 3 miles out, altitude 400 feet, traveling at 300 miles per hour. The director calculated a solution. The guns swiveled to engage. They fired 8 rounds before the fighters were past, already hitting the convoy. The shells burst at altitudes the aircraft had left seconds before. No hits, no damage. The fighters strafed the convoy, destroyed 2 trucks, and vanished back into the clouds. Standing in the gun pit, watching smoke rise from the burning trucks, Reeves felt a strange dissonance. The system had worked, the radar had tracked, the director had calculated, the guns had fired on command. But the mathematical precision that made the system revolutionary at high altitude became a liability at low altitude, where the targets moved too fast and the engagement windows were measured in seconds rather than minutes. Captain Halloran, after reviewing the engagement, made the decision that commanders across the front were reaching simultaneously. When the Luftwaffe came low, they would fire manually, using the radar for detection, but relying on the crew's eyes and instincts for tracking. The system that had made them dependent on mechanical calculation was, temporarily, set aside in favor of the skills they'd almost forgotten. The weather broke on December 23rd. The clouds lifted to 3,000 feet, then 5,000, then cleared entirely, revealing a cold blue sky that stretched from the English Channel to the German border. Within hours, Allied aircraft filled that sky, fighters, fighter bombers, medium bombers, thousands of sorties hitting German positions, supply lines, and reserves. The Luftwaffe, attempting to contest this aerial onslaught, threw everything it had into the sky. For 3 days, the air war over the Ardennes reached an intensity not seen since the Normandy invasion. German fighters Bf 109 seconds, Fu 190 seconds, even some of the new Me-262 jets engaged Allied aircraft in running battles that painted contrails across the winter sky. For the radar-directed anti-aircraft batteries, these were ideal conditions: high-altitude targets, clear weather, aircraft that had to fly straight and level to engage their targets. The SCR-584 and M9 systems, which had spent a week functioning as expensive detection equipment, returned to their designed role. Reeves's battery, during a 4-hour period on Christmas Eve, engaged 14 separate targets. They fired 163 rounds. They achieved 7 confirmed kills, 4 BF 109 seconds and 3 W 190 seconds, and 3 probable kills, where the aircraft broke off trailing smoke but disappeared before crashing could be confirmed. The success rate was extraordinary, even by the system's established standards, but it was what happened that evening, just before dark, that revealed both the system's capability and its ultimate limitation. A formation of Ju-88 bombers, 6 aircraft in loose trail, approached from the east at 16,000 feet, heading toward Allied positions around Bastogne. They were flying in weather that was beginning to deteriorate again, with scattered clouds forming at 10,000 feet. The radar acquired them at 18 miles, tracking them steadily as they approached. Morrison, in the Director trailer, called out the engagement parameters. Multiple targets, high altitude, bearing 095, solution calculated for lead aircraft. Guns ready to engage at 12 miles. The guns elevated to the calculated angle, the crews were loaded. At 12 miles range, with the formation still barely visible as dark specks against the darkening sky, the electrical firing circuit closed and the first salvo departed. What happened next was recorded in the battery's war diary with clinical precision, but to the men who witnessed it, the sequence seemed almost unreal in its mechanical efficiency. The Director locked onto the lead bomber and fired continuous salvos, 4 rounds, 5 rounds, 6. On the 7th round, the radar return from the lead aircraft flickered and disappeared. The Director, without pause, shifted to the second aircraft in the formation. More salvos. 10 rounds later, that return disappeared. The Director shifted to the third aircraft. The entire engagement lasted 4 minutes. The battery fired 68 rounds. 4 of the 6 bombers disappeared from the radar screen. The remaining 2 broke formation and turned back east, and the Director, following its programming to prioritize the most dangerous targets, let them go in favor of re-engaging with other threats in the sector. No one in the gun crew saw the bombers fall. It was full dark by then, and the aircraft had been miles away, visible only as radar returns on Morrison's scope. But 4 bombers had entered the coverage zone, and 4 bombers had ceased to exist as radar returns, and the mathematics of cause and effect were unambiguous. Captain Halloran, climbing out of his observation position, found Morrison making his usual notes. "How many tubes did that burn out?" he asked. Morrison looked up, his face exhausted. 6. But that's not the issue anymore. What is? Morrison gestured toward the radar antenna, still rotating in its endless circle. "We're running out of targets," he said. "The Luftwaffe can't sustain these losses. Every time they come up, we kill them, and they're learning." Morrison was correct. The air war over the Ardennes marked the Luftwaffe's last significant effort to contest Allied air superiority in the West. The losses, both to Allied fighters and to radar-directed anti-aircraft fire, were unsustainable. In the final week of December alone, the Luftwaffe lost more than 600 aircraft over the Western Front. Pilots who survived reported that flying over Allied positions was suicide, that the anti-aircraft fire seemed to follow them through maneuvers, that aircraft simply disappeared in bursts of flak that appeared exactly where they were about to be. By January of 1945, German air activity over the front lines had diminished to isolated reconnaissance flights and desperate ground attack missions flown by pilots who understood they probably wouldn't return. The systematic bombing raids, the massed fighter sweeps, the coordinated efforts that had characterized Luftwaffe operations earlier in the war, all of it had been ground down by attrition, fuel shortages, and the simple mathematics of a technology that killed more efficiently than the enemy could replace losses. The SCR-584 and M9 systems had not single-handedly destroyed the Luftwaffe fuel shortages, the Eastern Front's demands, and Allied fighter superiority all contributed. But the radar-directed guns had made the cost of operating over Allied positions prohibitively high, turning what had been dangerous into what was effectively suicidal. For the men operating the systems, this success created its own strange melancholy. They had trained for war, had been given weapons of unprecedented effectiveness, and now sat in positions where the enemy no longer came. The guns still fired occasionally at reconnaissance aircraft, at the occasional fighter bomber, at Vone 2nd and later V2, rockets that radar could track but not intercept. But the sustained engagements, the multi-target nights, the feeling of being essential to survival, all of that faded as the air war moved east and then ended entirely. The European war ended on May 8, 1945. Reeves's battery, by that point positioned in southern Germany, had not fired a combat round in 3 weeks. The SCR-584 radar still rotated, scanning empty skies, tracking the occasional Allied aircraft and identifying it as friendly through the IFF transponder system. The M9 Director, its tubes finally replaced with fresh units after months of degraded operation, calculated firing solutions for targets that no longer existed. Morrison, still with the unit despite having no official reason to remain, spent VE Day in the Director trailer, running diagnostic tests. Reeves found him there in the afternoon, hunched over his voltmeter, checking circuits that would likely never be used in anger again. "What are you doing?" Reeves asked. Morrison didn't look up, making sure it still works. "Why does it matter? War's over." "Because," Morrison said, setting down his tools, "this matters more than the war. What we built here, not just this system, but the idea of it changes everything. The next war won't be fought with optical rangefinders and manual calculation. It'll be fought with radar and computers and guided weapons that think faster than humans can. This is the beginning of that." Reeves looked at the maze of tubes and wiring, the oscilloscope screens, the mechanical calculators whirring quietly in their eternal loops. "You think there'll be a next war?" "Always is," Morrison said quietly. "The only question is whether we'll be ready for it." The post-war analysis of the SCR-584 and M9 systems' performance filled volumes. The statistics were compiled, studied, argued over by military theorists and weapons designers trying to understand what had worked and why. The numbers were stark. In the European theatre, batteries equipped with radar-directed fire control achieved kill rates 10 to 15 times higher than conventional systems. The average shells per kill ratio dropped from over 2,000 to approximately 150, still significant expenditure, but representing a revolution in effectiveness. In terms of deterrent effect, the radar systems had virtually shut down German air operations over Allied positions in the final months of the war. But the deeper significance lay not in the statistics, but in the principle the system represented. For the first time in military history, the loop of detection, decision, action had been closed by machines that thought faster than humans could. The radar detected, the computer decided, and the guns acted, all at speeds that made human cognition a bottleneck rather than an asset. This principal automation of the decision cycle would define military technology for the next 70 years. The SCR-584 and M9 were primitive by later standards. Their vacuum tube brains slow and fragile, their mechanical calculators crude. But they established the template. Sensors feeding data to computers, feeding instructions to weapons, operating at speeds that made human intervention optional or even detrimental. The next generation would bring digital computers, solid-state electronics, and integrated circuits. The guided missiles that Morrison predicted would arrive within a decade. Nike, Ajax, Hawk, Patriot, each one building on the principles demonstrated by the radar-directed guns of World War II. The automation would grow more sophisticated, the decisions more complex, until eventually the human role in the kill chain became one of oversight rather than operation. The philosophical question whether machines should be making life and death decisions was rarely asked in 1945. The system worked. It saved lives. It won engagements. That was sufficient. Sergeant James Reeves returned to civilian life in November of 1945, discharged from an army that no longer needed millions of men in uniform. He worked in construction, married, raised 3 children, and rarely spoke about the war except in general terms. When his son, in 1968, received his draft notice for Vietnam, Reeves finally told him about the radar guns, about firing 200 rounds in an hour at targets he never saw, about the strange experience of becoming a servant to a machine that thought faster than he could. "Did it bother you?" his son asked. "Letting the machine do the fighting?" Reeves thought about that for a long time. "It saved my life," he finally said. "Probably saved a lot of lives. But there was something, I don't know how to describe it, something lost when the war stopped being about what you could see and became about what the machine told you was there. You fired at a blip on a screen, and sometimes the blip disappeared, and you never knew if you'd actually killed someone or if they'd just flown out of range. It was clean, efficient, and that efficiency was the thing that bothered me most. The SCR-584 radar units and M9 directors were decommissioned in the years following the war, replaced by newer systems with digital computers and more sophisticated tracking. Some units ended up in museums, their vacuum tubes and mechanical calculators preserved as artifacts of a transitional moment. Others were scrapped, their components recycled, their innovations absorbed into successor technologies that made them obsolete. Morrison, the civilian engineer who'd spent 2 years keeping the systems operational, returned to Bell Laboratories and continued working on radar development. He was part of the team that designed the Nike missile system and later the early warning radar networks that would form America's nuclear defense perimeter. He died in 1973, having spent 3 decades refining the principles he'd helped prove on European battlefields. The legacy of the radar-directed anti-aircraft system is visible in every modern military technology. The principle of automated fire control sensors detecting targets, computers calculating solutions, weapons engaging without direct human aiming has become so universal that it's difficult to imagine warfare without it. Fighter aircraft track targets with radar and fire missiles that guide themselves. Naval vessels engage threats beyond visual range. Ground-based air defense systems can simultaneously track dozens of targets and engage them in order of priority, all automatically. The ridiculous radar predictor that let a single battery track 8 targets and fire 200 rounds in an hour was, in retrospect, not ridiculous at all. It was inevitable, the logical evolution of warfare toward automation and precision. What seemed like magic in 1944 became standard procedure by 1964 and obsolete by 1984, surpassed by technologies that made the SCR-584 look as primitive as the optical rangefinders it had replaced. But in the winter of 1944, on cold nights over Anzio and Antwerp and the Ardennes, when German bombers came and the radar antenna rotated and the guns fired in their mechanical rhythm, the system represented something genuinely new, a partnership between human and machine, where the machine did the thinking and the human did the loading, and, together, they achieved lethality that neither could manage alone. The war that had begun with men cranking traverse wheels by hand and estimating altitude by eye ended with guns that aimed themselves and shells that burst exactly where mathematics predicted they should. The distance between those two realities was measured in only 5 years, but it represented a chasm in military technology that would never be crossed back. Sergeant Reeves understood this, standing in his gun pit on VE Day, looking at the pile of spent brass casings that represented 200 engagements and thousands of rounds fired. The machine had made him more lethal than any soldier in history. It had also made him, in some fundamental way, less essential. The future would belong to machines that thought faster, saw farther, and killed more efficiently. The human role would be to maintain them, load them, and trust them. He had survived because of that trust. But survival, he was learning, didn't always feel like victory. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.